In the last video, we took a look at the conditions for equilibrium and worked a few examples. And mostly because I didn't want that video to get too long, this video is just going to pick up a couple of additional topics. First one I want to visit is stability and balance. So here, let's think about, say you're driving a car at posted speed limits, of course, but unfortunately the traffic engineers didn't do a very good job of calculating what an appropriate speed limit should be. And so you're going around the curve and you find suddenly that one of your tires comes off the ground. So it'd be natural to ask, how high of an angle could you possibly be tilted up and be stable? And what I mean by stable here is that if you got yourself tilted up like this, that you would end up still wanting to twist back down the correct way instead of rolling over. Well, we can go ahead and we can just use the car right here and draw an extend free body diagram on top of it. So let's say the center of gravity is located here. Well, then we would have a force of gravity acting right here. And then here at the contact point of the tire, we'll have a normal force acting up, and those are our only two forces. And as drawn here, it would probably make the most sense to put our axis of rotation here. So we would have no torque due to the normal force about this axis. And we would see that we would indeed have a clockwise torque due to gravity about this axis. And so hopefully the car will come back down right side up. No guarantees about how the suspension is going to do, but at least you avoided having a rollover. Now let's say the car got tilted just a little more. So the limit of our stability is, and here I'm just trying to draw the car even just a little more tilted. Well, sorry. I'm sorry, that's just too awful even for me. Let's try that again. So we're even more on tilt than we were before. So there's one of our tires. Whoa, what was all that about? So there's one of our tires there. Car. That's supposed to be a steeper angle. Yeah, it is just a little bit. So at our maximum here would be when the center of gravity of the car winds up being perfectly over that contact spot. So there's force of gravity down, normal force up. We'll go ahead and continue to put our axis of rotation in the logical spot, but now the issue here is that the lines of force of both forces cross through the axis. There is no torque. So we will say that the angle at which the car is tilted for that to happen is the critical angle. If we get twisted even more, then the center of gravity would be to the left of the contact point on the tire. And so instead of trying to return back to normal, you would flip the other way and be at risk for a rollover. So let's draw in some dimensions here. So let's say that the space between the wheelbase is t, and we will say that the height of the center of gravity above the wheelbase, or above the wheel contact point here, is h. All right. So in this perfect lineup here, our center of gravity is sitting right over our axis, like so. So then if I extend out here at my critical angle, this distance here to the perpendicular would be h. And this distance here would be 1/2 the width of the wheelbase, t over 2. And you can do a little bit of geometry to convince yourself that this angle here is also that angle there. So this is also the critical angle. So then we can say that the tangent of the critical angle is equal to t over 2, that's the opposite, over the adjacent h. And I can multiply both numerator and denominator by 2 to make that t over 2h, make that look a little prettier. Then finally, to get the critical angle, we end up saying that it is equal to the arctangent of t over 2h. Now, as the argument of an arctangent gets bigger, the critical angle gets bigger. So there are two ways that you can make a vehicle more stable. Because a more stable vehicle would be one with a larger critical angle, because you could tilt the vehicle at a higher angle and have it still flop back down to the safe position instead of rolling over. So the two possibilities are you could make t bigger, so that's making the wheelbase of the vehicle bigger, or the base of support of whatever the object is. It doesn't have to be a car. So you can have a bigger base of support, and you'll see that sports cars typically are wider than normal passenger vehicles, and that is to increase the width of the base of support to make it harder to flip the car over. The other way you can do it is you can make this number here, h, in the denominator smaller. So you can, if you can lower the center of gravity with respect to the wheelbase, it'll again be harder to flip over. This is part of why there's been a lot of work done with pickup trucks, because since pickup trucks naturally sit high, there's been a lot of work done to try to shift components of the vehicle lower, make the wheelbase wider, everything you can to make it harder to flip, just because this height of the center of gravity for a pickup truck is typically higher than for a passenger car. In the other extreme, electric vehicle manufacturers who are designing a vehicle from scratch rather than trying to take an existing vehicle design and stick electric pieces in where the equivalent gas pieces were, take a novel approach to design the vehicle. What they do is they stick the battery pack right at the bottom of the car. The battery pack is typically over half the weight of the car, and by doing that, you can have the center of gravity of a vehicle be maybe 18 inches off the ground, something like that. You can have quite a low center of gravity, just taking advantage of the fact that these battery packs are incredibly massive. So if you put it as low as you can in the car, at least one way to make lemonade out of the lemons is that it makes it incredibly hard to flip the car over. Okay. So the other point that I wanted to get into was just purely to introduce Hooke's law. So this is describing elasticity. And there is a bit of an interesting point about this. That it turned out that Hooke did a lot of exploration with this because he was exploring the possibility that this could be an accurate model of gravity. Turned out not to be, but is a very accurate model for springs. So it turns out that if you have a spring, so let's say here's a wall, I got a spring here. The spring will have a natural length that it wants to be at, unstretched. So if you stretch it, say like this, what will happen here is that if there's something attached to the end of the spring, it will feel a force to the left as the spring tries to pull it back. And similarly, if you compress it, you'll feel a force to the right because it's trying to get back to its original length. Now, it turns out, we'll call this amount of stretch here delta x. And usually the way this is done is we'll say that this is delta x equals 0 at the unstretched length. If you are pulling off to the right here, this would be delta x is positive. Over to the left here is delta x is negative. And so it turns out that as long as you don't go crazy stretching a spring, for at least moderate spring stretches, and then for longer ones, if you are deliberately engineering the spring to have this property, it's very achievable. It turns out that how hard the spring pulls is directly proportional to the stretch. So we can just say that the force of the spring is equal to minus k delta x. Now, this minus sign here, because what I'm doing here is I'm taking the x component of this, if you will. This minus sign here, don't sweat this. Usually what I recommend people do is just work in magnitude and use their common sense to figure out whether the spring is pushing to the right, is either going to the pushing to the right or to the left. But what this is taking into account is if I stretch the spring, so I pulled it to the right here, delta x is positive, but the minus sign means I'm pointing to the left. And if I compress it here, delta x was negative, but the minus sign makes it positive, so the force is to the right. So this minus sign is here to bake the direction into the cake. And we will need this when we get in a while, when we get to simple harmonic motion, we will actually have to mathematically worry about that minus sign. But in any other situation where you see a spring show up, don't sweat the minus sign. Just use your common sense. So this k here gets called the spring constant. And it depends on the details of how the specific spring was manufactured. The units of it are newtons per meter. And springs can be all over the place. Delicate watch springs might have a spring constant of like 1,000th of a newton per meter in some extreme cases. On the other hand, you can get to ridiculous cases the other way. In earthquake zones, sometimes skyscrapers are actually at the bottom of the foundation, are set on giant concrete springs, concrete and rebar. And these springs have a ridiculously high spring constant on the order of billions of newtons per meter. But that should give you some idea of a range. So just to do one quick example just to make this seem a little more concrete. A typical application would be, say, to use a spring scale for measuring mass. So here we go. We'll stick some mass here. What we want is we want it so that every centimeter of stretch corresponds to adding 100 grams. So let's just say I put on 100 grams, not kilograms here, 100 grams here. What we want in that case is for delta x to equal 1 centimeter. So we need to figure out what would be the appropriate spring constant to make that happen. Okay, so we can do a force identification diagram here. So we cut through the spring, so now we've got a spring force, and that's it. Our only long-range force is gravity. So we can go ahead and do Newton's second law in the y direction. For our spring scale, the acceleration will be 0. Taking the y component, we will have the force of the spring up, gravity down. So this is what I'm saying. Now here, when I put in, I'm not going to bother putting in the minus sign. When I put in for the spring, I'm just going to say k delta x because I've already baked into the cake that it's pointing up, and I'm only interested that the magnitude of the stretch is 1 centimeter. And minus mg equals 0. All right, so we get that our spring constant would be mg over delta x. So we said 100 grams, so that's 0.1 kilograms, 9.8 newtons per kilogram. And we wanted a 1 centimeter stretch, so that's 0.01 meters. Alrighty, well that works out to be, the kilograms cancel, we'll be left with newtons per meter. 0.1 over 0.01 is equal to 10, so this gives us 98 newtons per meter. Alrighty. So with that, going forward here, we will start taking a look at momentum. So have a good one.